It's all yours.
So you went to Tufts?
I did, yeah.
I watched Tufts win the D3 lacrosse championship a few years ago.
What's that?
I said I watched Tufts.
Oh, yeah?
Yeah, win lacrosse.
Geez, I never thought of them as being particularly good at sports, but lacrosse, I guess, fits with Tufts.
All right. So today we're pleased to have Mike Watts here. Mike graduated from the small technology school in Massachusetts, where he subsequently returned to as a professor. So we're glad to have him here. He's attendee in the intervening years, and I think you've all seen the images of MIT they've done with their 3D scanner, which is very impressive. So Mike, talk about low power and large scale microphotonic circuits. Thank you.
Thanks, John, and thanks for the invite. So I'm going to be talking about our efforts towards low power and large scale microphotonic circuits, and as you'll see, these two things go hand in hand. But before I go into the microphotonics aspect of the work, I think it's worth stepping back and looking at what happened with transistor scaling over the years. So if we take ourselves back to the mid-1970s, the largest microprocessors only had about 10,000 transistors in total. And you can ask yourself, if you were a researcher working for Intel back then, would you have expected to have gotten to 5 billion transistors today? So I think that's an interesting question to ask yourself as we think about microphotonics and scaling into the future. I think it's also interesting to think about the fact that, of course, we're all very familiar with Moore's law type scaling, and of course for CMOS and microprocessors, this has really been the most successful form of scaling. But there's been scaling in other technologies as well, right? So if we look at focal plane array imagers, the pixels have gotten smaller, but the arrays have actually also gotten larger. So it hasn't been just a continual shrinking of detectors. The same thing with displays. If we look at displays, a 10K display now has something like 10 million pixels. And the displays have gotten larger. The LCDs have gotten a bit smaller. So when you think about scaling in general, what's required? And really it seems to be that one of the primary features is that you have some unit cell. And this unit cell element can be very accurately modeled. And it's not just modeled on a single element basis, but that you can cascade many of these elements typically. And that you can also reliably fabricate these unit cells. The unit cell itself, of course, has to be very low power, because if it's not low power, then the power consumption of the unit cell will limit your scaling by itself. And then, of course, you need a really compelling application. And of course, computers, cameras, and displays are very large markets that can really drive a technology forward. So think about these things as we think about microphotonics. And when I think about microphotonics, it brings me back to my graduate school days, and maybe that's just because that's when things started for me. But I think really in the late 90s, microphotonics was just emerging. So I had joined the house group at MIT in '99, and Herman House and Brent Little, who later formed Little Optics, were Brent was just leaving MIT, and they were working on ring resonators, and some of their rings were in silicon with silicon dioxide claddings surrounding the silicon. And this very steep index contrast that really makes for the ability to make really tight bends and really tight confinement of the optical mode. And so we're looking at bend radii that are down around 2 microns. And if you compare that to the silica waveguides, which were dominating the telecom industry at the time, their bend radii were about 2 centimeters. So you're talking about a factor of 10 to the 4 reduction in bend radius, or in terms of area, component density, you're now talking about a factor of 100 million greater potential component density. Of course, you need to be able to do something useful with these very tight bends, and the probably most well-known thing, of course, you can simply wrap these bends around into a ring. If you have an integer number of wavelengths that fit within that ring, then you form a resonance. And of course, you can cascade these resonators, coupling one to the next, and coupling to the output waveguides, bus waveguides, to form nice flat-top filter functions. And of course, this is key for wavelength division multiplexing, or at least opening up that possibility for WDM communications on chip. And then, of course, we're all striving towards integrating silicon photonics with CMOS. So it has some nice features, but I think it's still, of course, important to step through. Does it have the ability to simulate, fabricate? Is it low power, et cetera? So let's first look at, can we simulate microphotonics well? And of course, you're all very familiar with this. We can. I mean, we can launch modes into a simulation domain. This is a three-dimensional FDTD simulation, and you can then take mode overlaps and use those mode overlaps to develop a scattering matrix for a particular element. You can then cascade these elements and form nice flat-top filter functions. Actually, in this device, it's about a third-order ring. It turns out that if you, in fact, if you don't take into account the fact that the center ring sees a different external dielectric than the side rings, then you end up with a frequency mismatch of the center ring. So you actually have to make the center ring a bit larger. But you can actually take all of this into account. So this is a third-order triple-stage filter. The design was led by my colleague, Miloš Popović, who's now at Boulder. This thing is constructed such that these second two stages actually give you deeper and deeper extinction ratio in design. But you can see we can now actually load the center ring. So actually, we used a greater e-beam dose on that center ring in order to get matched frequencies across all three of them. And you can see the experiment matches up with the design quite nicely, and we can get nice extinction in both design and experiment. And so this holds. So you can, of course, design these components, and you can do more intricate things. So this is I'm skipping over a lot of details on the design on this component, but this is a polarization splitter and rotator. This was my thesis work years ago, where we take the random polarization state coming from a fiber, and we split off the TE component, or sorry, the TM component, and then we adiabatically rotate that to be TE on chip, so that only TE light exists on chip. So you can see this in the IR images. As we put in TE light, we get light out of the TE port, mixed polarization, light out of both ports. And then TM light, we get light out of the TM port. And it is, in fact, rotated in polarization. So you can do some fairly intricate things. You can even combine these structures. This is a circuit I designed which had both of these structures in there. It first separates the polarization states, rotates one so that all we have is TE on chip, sends the originally TM component to this filter bank, and the originally TE component to this filter bank, and recombines them through the reverse process. And we were able to achieve polarization independence on chip. This was all done painstakingly by hand. So literally, going through and taking mode overlaps of each of these components, assembling the transfer functions. And this works up to a certain point. So here we have about 30 components on chip. But then when you start going into now having not just passive silicon photonics, but active components, and active components that are now stacked on top of CMOS, which is what we have in the upper left here. This is a silicon waveguide, and this is still silicon, but underneath here there's actually germanium detector. So what's happened here is there's a wafer of our processes. We have a wafer of silicon photonics and a wafer of CMOS, and the silicon photonics is bonded on top of the CMOS. We then go in and remove the handle wafer and drill down vias. So in total, we have our 20 silicon photonics layers plus another 30 CMOS layers, and then 5 layers for 3D interconnections connecting up the circuits to the photonics. So just actually visualizing all of that is actually a lot to handle. And then, of course, you need to be able to go through and have automatic design rule checkers to make sure that everything is actually interconnected correctly. And then ideally, you want to be able to simulate everything in one environment. So we chose to use the electrical simulation domain using Verilog A within Cadence. And we sort of forced our photonics to work within this framework. So here we have a CW laser, and you can see the very high frequency carrier. We then have a PRBS voltage source that's then driving a modulator. You can see the modulator voltage turning on and off and modulating the optical field inside the modulator. Then as the field leaves the modulator, finally as it passes through a ring resonator filter and ultimately goes to a receiver. And in this way, you can get to a simulation environment that's scalable. And of course, that's critical to getting to complicated circuits. Equally important is an ability to fabricate in a scalable way. And E-beam fabrication, while nice and quick, and it gives you high resolution, it's a serial approach that does not lend itself to the scaling that's needed. So we've moved to a 300 millimeter fab, a standard CMOS fab that sits in Albany, New York. And actually even using relatively inexpensive masks, just simple chrome on glass masks, we can get sub 100 nanometer lines and gaps. If you take full advantage of their phase shift masks and proximity corrections, you should be able to get down to something like 20 nanometers at a cost of something like $50,000 a mask level. So we haven't gone to that step at this point. But it is and not just us, but the industry in general is moving towards producing everything in CMOS fabs, and of course that lends itself to mass production. So, of course, as I mentioned, we need to have a low power unit cell. And now with photonics, it's a bit difficult to define a single unit cell. So I'm going to step you through one component that I spent a lot of time on reducing the power of. And just with that example, say that, of course, over time, a lot of these components can be driven down in power. The component I worked on was the Silicon Modulator. And silicon modulators, which I'm sure you're very familiar with, work on the fact that you have an ability to change the carrier concentration in silicon. And in changing the carrier concentration, you change the polarizability of the material or the plasma frequency hidden in here of the material. And that changes the refractive index. And of course, as you have larger changes in carrier concentration, you get larger changes in refractive index. But if you look at the scale of the changes we're talking about in silicon, this is a fairly weak effect. And so you're tempted to focus on injection-based devices because you can drive a large number of carriers into the device. The problem with silicon in injection-based devices is that you have a very long free carrier lifetime, and that limits the speed of operation. So we've actually focused more on depletion-based devices, which I'll talk about. In getting to a low power component, one of the key aspects is you have to have a small component. I think it's kind of universally true. And so I'm pointing to some modulator work by the Cornell group, McCall Lipson's group, not because it was the first silicon modulator, it wasn't, but because it showed a path to getting to low power modulators just because the size of the component was greatly reduced. So this is a ring resonator based modulator, and it was an injection based device which limited its speed, so it was something like 1.5 gigabits per second, and it also made it actually not that low in power. It was on the order of 10 picojoules per bit due to the fact that you're driving so much current into it. But it did lead a path towards getting to low power. So we took a look at this device and looked at some of the previous work on depletion-based Mach-Zehnder modulators and just asked the question, if we were to try to make a depletion-based ring modulator, how would we go about doing it? How would we get the lowest power consumption? And it turns out that, of course, what matters is how much charge you're adding or removing to the volume, right? Because that's effectively the carrier concentration. So that gives you the change in carrier concentration. Well, that turns out to be just simply CV over the volume. So when you look at that and you ask yourself, well, what do I want to do here? I want to have the largest frequency shift possible, but I also want to maintain a low voltage because we want to have a low operating voltage for CMOS. But also, if you look at the energy that's consumed in charging and discharging this device, it goes as CV squared. So you're better off increasing the capacitance than increasing the voltage. So it turns out you actually want the largest capacitance per unit volume to get the largest frequency shift per applied voltage in a depletion-based device. And then you have choices in how you can structure these devices. You can use a lateral junction device, or you can use, for example, a vertical junction device. But if you look at the capacitance per unit volume, in the same size structure, the capacitance of the vertical junction device is 2 to 3 times that of the lateral junction device, just based on the area of the PN junction. The other nice thing is that if you go to a vertical junction device, you can actually keep your contacts in the interior of the structure. So in a lateral junction device, you have to have your contacts, one on the inside and one on the outside. And that means you have to have a ridge waveguide structure. That opens up a radiation path that limits the size of these devices. By keeping the contacts directly in the interior, you can have a full cut through your silicon, which confines the mode much more tightly. And so actually you can maintain a volume that's 6 to 10 times smaller than the lateral junction devices. So you can increase the capacitance per unit volume without actually increasing the capacitance. This work started for me at Sandia National Labs when I was a member of technical staff there. And we started with a structure that was very simply contacted. It was a vertical PN junction contacted in the center. And we used N plus and P plus plugs to contact the PN sides of this junction. And then just simply operate in depletion mode, using that to modulate the depletion width in the device. And you can see the frequency shifts that we achieved. So at about 3.5 volts, we got nearly complete extinction. And this is running at 10 gigabits per second with 3.5 volts applied. And you can see that we have very low loss. This is the actual one. And decent extinction. So at this point, it was down to about 60 femtojoules per bit. So that's certainly much less than 10 picojoules. And of course, that's largely owed to the fact that it's a depletion-based device. We then looked at our structure and decided that structurally there's a problem. And we kind of knew this when we made it, but it saved a math step, which is that we don't need to have a PN junction over the whole structure. And instead, we just could put a PN junction on the outside region, which we did. But then we also looked at, what happens if we dope all the way around the structure or dope halfway around? And you would expect that if you dope all the way around the structure, that you would get twice the electro-optic shift. But when we actually looked experimentally, we did not. We only got about 50% greater shift. So that turns out to be due to the fact that there's a lot of resistance pulling the carriers from these outside edges. And it's that resistance that is it's effectively dropping voltage or causing the electric field to decay as you go to the outside edge. So out here, you have a smaller voltage across the junction. So we actually just half-doped these structures, and these are the results we got at 1 volt drive and 1.5 volts. And we were able to drop the voltage primarily not because of the design change, but more because of the fact that we decided that if we use the structure in accumulation mode, you get a larger frequency shift for a given applied voltage. And this is because the depletion width goes as the square root of the voltage plus the built-in potential. So as you drive this close to 0, then you get the largest frequency shift for given applied voltage. So at this point, we were down to something like 3 femtojoules per bit with a 3 dB extinction ratio. And then more recently, we switched to the 300 millimeter fab. And in doing so, we put 2 levels of metal in. And what 2 levels of metal did was allowed us to actually contact the structure in the center and then have a contact that's radial or circular around the outside. And in doing that, that lowered the resistance in the structure further. So now we can, we also had some doping changes. I think the doping increased by about a factor of 2. But we can now drive the device with just plus or minus 0.25 volts and drive it up to 25 gigabits per second using less than a femtojoule per bit. We can go to 44, but we have to quadruple the voltage applied, so it's at some power consumption cost. So it's just tracking a case of going from picojoules down to femtojoules in one photonic component. And of course, I think there's a lot of work to be done on numerous components, but at least shows one example of photonics being very low power. The last piece, of course, is we need to have a compelling application. And I think for those of us in the field, we've all pointed to the world's data centers and supercomputers as a compelling application. And there is no doubt that it's a compelling market application. I think that's increasingly clear. But it's not clear that it's a compelling application for scaling the number of components quickly. And the reason I say that is that if you look at the largest switch processors, they have something like 4 terabits per second coming in and out of the switch. And when you lay out your silicon photonics and you've got all your components, in this case, I'm assuming an off-chip, WDM laser, and you demux and encode data onto a wavelength and mux it back out, and sort of in the reverse, you demux the data and detect it. When you add up all of those components, for 4 terabits per second, you're talking about something like a couple hundred links, and this is probably an overly complicated view of how many components you need, but something like 1,000 components overall. So not that that's a small number of components by today's integration standards, but it's not getting you to the millions of components quickly. So then the question to ask is, what about on-chip links? And for those of us that have spent time looking at on-chip links, it's a tough case to make because on-chip, the electrical communications are fairly efficient. So you're looking at something like 100 femtojoules per bit per millimeter, and of course, laying out wires seems a lot easier than putting down photonics. And on the other hand, when you look at very advanced nodes, something like maybe the 8 nanometer node and a large server processor, flowing across that processor is up to something like a petabit per second. And if we just look at the power consumption of that communications, we're looking at something like 100 watts at the 8 nanometer node. And so that's quite substantial. In fact, you would like to have the whole chip consume no more than 100 watts. So if you can make your photonics sufficiently low power, and of course after photonics matures a bit so that it's not that much harder than putting down wires, then this actually becomes a compelling application, and it would drive scaling. So at a petabit per second, we're looking at something like a couple 100,000 components as a sort of starting point. So that's interesting, but of course you also have to deal with all of the components on the link and ensuring that they are low power. And one of the primary criticisms of the ring resonator work is that, of course, as you have cores turning on and off, they're going to adjust the frequency of the rings. And not only that, just the room temperature changing is going to adjust the frequency of the rings. But actually, I think it's not just about ring resonator-based modulators, but no matter what filter you put on, if you're going to do WDM communications, you have this problem regardless. So you have to solve it. We spent a lot of time looking at trying to put heaters directly into our rings. And the first problem we ran across was, well, how do you actually put a heater into a ring? We didn't want to heat the cladding directly. That's what we had seen in the literature before. And the problem with that is you get a lot of thermal spread. So we tried to actually contact our rings as a first step. And the problem is, of course, if you contact a ring directly, it introduces a lot of scattering and loss. But it turns out that if you adiabatically widen your ring prior to making contact, you can contact it where there's essentially no optical fields, and you can get almost complete transmission through 180-degree bends. Now, that in some ways makes sense because I'm sure you're worked a lot on adiabatic devices, but the thing that's surprising is how rapid this adiabatic transition can be. So even just a 2-micron radius bend works quite well, and it turns out to be for 2 reasons. One is that the coupling between this fundamental mode and the next available mode, which starts to be guided maybe around here, is very weak because the overlap is at the interior of the rings. The coupling coefficient is small. And the other piece is that they propagate at very different rates. And what matters for an adiabatic device is the ratio of the difference in the propagation constants to the coupling coefficient. And since that ratio is very large, you can make a very compact adiabatic bend. And you can see you can make this is a 4-micron diameter, 2-micron radius resonator, and with a theoretical Q of 10 to the 4 or 10 to the 5, which is sufficiently high for communications applications. The other nice thing about this structure is that where you couple to the device, it's actually single mode. So when you look in the frequency domain, you see that you have no unwanted modes in the structure. So it's a nice uncorrupted free spectral range. OK, now getting to how we actually put these heaters into these devices. So we use these adiabatic bends so that we can now make contact with the rings, and we can make these sort of arduous silicon tethers back to our vias, and those arduous paths give us thermal isolation. We can then drive a current through the ring if we've doped a small region inside, and then heat the ring directly. And this gives you the least thermal spread, the lowest heat capacity, and therefore not only low power devices, but pretty fast devices. So they're sort of 1 microsecond time constant. You can tune all the way across the free spectral range. And this is both experimentally and in simulation. It's about a microsecond device. But they still consume 44 microwatts per degree C, or I think this is a 10 gigabit per second rate, but something like 44 femtojoules per bit. And if you can think of your link, you're going to have several of these. So it's not insignificant when you're trying to get below 100 femtojoules per bit. That said, you can use them. This is an automatic locking loop where we put this into a control loop and automatically locked on to a laser line. It took this wasn't optimized. It took maybe a tenth of a millisecond to actually lock, but it did work. We've also put in temperature sensors into our rings. This is a heater modulator. This is a modulator with a heater and a temperature sensor built in. You can see it's starting to get complicated. In fact, in this device, if I remember correctly, the modulator did not work well. But nonetheless, we were able to actually hold the resonant frequency constant over 55 degrees C change of the substrate temperature. So the general approach works. But when you look at these devices with all these contacts built in, and the fact that you're now using some area for your heater and some area for your modulators, you find that while generally your filters are okay, you've sacrificed somewhere. And in this case, we sacrificed a bit on our modulator performance, so we were able to get to about 13 gigabits per second, but you can see the eye is not as high quality. And so we asked ourselves, is there a better way to deal with this problem? And with our recent modulator results, we realized that in fact we have a large enough DC response that we can actually shift our resonant frequency by about 100 gigahertz just by applying a DC bias or changing that DC bias. So if we combine that, first of all, we can use that for a filter just by itself. We can deal with about 100 gigahertz of change. But actually, it turns out we can still modulate on top of that. So we can still put our half-volt AC signal on top of it, and we can modulate across 10 degrees C. So now, of course, in order for this to work in an application, that would mean that you would have to have your processor be able to hold its temperature to within 10 degrees C, which I think is reasonable, although today they're not designed that way. Or you would have to compensate for the thermal response of your rings in some way. So in fact, that they get less of a shift per degree C. But still, it opens up a path for a low-power approach to filtering and modulating. And then, of course, you need to be able to deal with the source and have an efficient source and also a cost-effective source. And of course, there's been some fantastic work here on the integration of 3.5-based sources. We've taken a different approach, not actually because of the communications problem, but because we're also on EFI and we're looking to make a mode lock laser, where we're trying to directly integrate erbium-doped aluminum oxide. So in this case, we're depositing erbium-doped aluminum oxide on top of silicon nitride. There's a small gap between the nitride and the aluminum oxide, but the general idea is that we have an inverted, sort of an inverted ridge waveguide. And the structure is shown again here in the upper left. You can see the modes match pretty well between the 980 and 1550 output wavelength, so the pump wavelength and the 1550 emission. And then, of course, we get some gain. It's obviously much lower than the 3.5 base structures, but we get a couple of dB per centimeter in these devices. And then we can lithographically adjust the output wavelength of these devices by just changing our grading pitch. In this case, we're going from about 15, I think we get down to about 1525 and we go out to about 1610. Our highest output powers are on the order of 75 milliwatts with slope efficiencies that are about 7%. So they're not as efficient as we'd like them to be ultimately. But the nice thing about erbium, and I saw some, or at least talked to someone today about some nice results here on this as well, is that their erbium has a gain which is largely temperature independent. So you can go over 100 degrees C and the gain doesn't change very much. I think I heard today even 300 or 400 degrees C may be possible, right? So that's nice. And the other thing that's nice is that the pumps are not temperature controlled, the commercial pumps today. So while you do have this quantum efficiency hit in using erbium, the fact that the pumps don't need to be temperature controlled, and that at least for the purposes of the gain, erbium does not need to be cooled, points to at least a potential for getting to about a 10% wall plug efficiency, which would be sufficiently efficient. And then finally, of course, you need to have some very sensitive receivers. Of course, the receiver power itself is something to consider, but the main point here is to drive the laser power consumption down. And if you have very low capacitance germanium or integrated detectors of any kind, if you can have a low capacitance connection out of that detector to your CMOS circuit, you can hang a large transimpedance gain at the receiver. And that means you can actually drive the Johnson noise voltage down because it's dependent, the signal noise ratio is dependent on the square root of the transimpedance gain. And in principle, you should be able to drive yourself from something like minus 18 dBm to as far down as minus 30 or 31 dBm, just because you can have a much larger transimpedance gain. So we think we're going to get to about minus 28. Our detectors are not actually 1 femtofarad. So this is just a snapshot of our process that we're working on overall. Most of this is complete or nearly complete. The final integration of the lasers is not there yet. We are in the process of bonding our silicon photonics to our CMOS now. So this silicon photonics is flipped. There's 2 levels of metal, germanium, 2 etches into the silicon, 2 levels of silicon nitride, and the 2 levels of nitride are actually for the erbium, and you can actually access this either way. So either you can, with the chip, with the wafers unflipped, one of these layers, when it's unflipped, it turns out to be the top layer ends up being an etch stop. So you can etch down controllably down to this layer, then remove the silicon nitride that's remaining, deposit your doped aluminum oxide. We can also then flip those layers in the reverse configuration so that you can etch down and stop controllably, deposit your doped aluminum oxide. If you put all this together for a link and then look at how much power you expect to use in the circuits and so forth, we think that at the 65 nanometer node, we should be able to get below this 100 femtojoules per bit. That would be required to make this equivalent in some ways to electrical communications. And as you go to more advanced nodes, you should be able to get close to 25 femtojoules per bit. But I think the nice thing is that once you're in photonics, of course, in the photonic domain, it's not just a 1 millimeter point-to-point link. You can communicate all the way across your processor chip, or even off the chip out to memory or out to the network. So it's more powerful than just simple wires on a chip. So that said, I'm not sure that'll be the technology that will drive photonics fastest. Of course, it's got a compelling market drive, but it's more complicated to implement than things like phased arrays. And we've spent some time looking at phased arrays, and of course there's been some nice work here out of Larry's and John's group on phased arrays as well. The basic principle, of course, is that with phased arrays you have simply an antenna and a phase shifter behind each antenna, and as you adjust the phase of these elements, you can change the emitted phase front out of the structure. Again, you can approach this in much the same way. You need to define yourself a unit cell. And in our case, our unit cell consisted of a very compact phase shifter. We wanted to, of course, minimize the size of our elements because, of course, the larger they are, the more grating lobes that you end up with. So ideally you want to be just half a wavelength, But of course, in photonics, everything's on one plane, so you're a little bit stuck with something that's bigger than half a wavelength. And so we, again, use one of these thermal phase shifters and adiabatic bends that could give us about 2 pi phase shifts in a reasonably compact structure. This is about, the repetition of the cells is 9 microns. So if we go from one edge here to the other edge, it's 9 microns overall. And then a very compact grating emitter. The nice thing about phase arrays, and why I think that, if the application is there, they may drive silicon photonics faster, is that you're replicating the same cell across a large area. And all that's really changing here is the coupling. So of course we have to, as we lose power coupling to each of these different rows, we have to increase the coupling strength to compensate for that. But otherwise, you're replicating the same cell. And this is just the example of an 8x8 active array that we made. And you can see the static pictures or the movie that you can steer up and down, left and right. Of course, there are these other lobes, and that's due to the fact that our unit cells are not as small as we'd like them to be. But generally, it worked the way we expected it would. The structure was just simply contacted in a row-column fashion. Actually, at the time, it's because I didn't want to pay for a more expensive probe, which probably was a mistake. But we wanted to show that we could make, first of all, a much larger structure so that this really scaled. And then we can make arbitrary patterns. And of course, in order to have arbitrary patterns, and if it's active, you can't, even if you bought the bigger probe, you're not going to buy thousands of voltage sources in order to drive it. So you really need to have CMOS behind it, or consider a static device. And so we implemented a static device where we're just adjusting the phase of each of these elements just by adjusting the length of the elements. And then you have to, of course, pick some patterns. So this is in the phase. These are the different elements, 64 by 64. And the different colors correspond to the different phase settings. And we used a phase retrieval algorithm to set these. And my student, as he was finishing his PhD, decided to, thought it was funny to pick his thesis committee as some possible patterns he could produce. But we went with the MIT logo. But what I think is interesting, though, is that at least Hank and Eric's likeness is quite close to reality. I think I look a little better than that personally, but it works reasonably well with 64 by 64 array. And you can see that, so our fiber's coming in up top here, and you can see that the last pixel that's illuminated, as you go down this, go all the way down this column or down this row and down this column to the last pixel, it's pretty much the same intensity as the first one. And of course, we're adjusting the coupling at each point. So not only is the simulation capability very accurate, but of course the fabrication is equally accurate. And then in the far field, this just tells you that the phase was well tracked through the system. So we kept track of the complex coupling coefficient at each point, and we were able to use that in our phase retrieval algorithm to produce the MIT logo. And you can produce other patterns. This is just a series of dots that we decided to produce. And you can do things like play with the amplitude of your emission. So nominally, we just have a nice flat top distribution of our emitters. And if you do that, of course, you take the Fourier transform as you go into the far field, you end up with a sort of dual sync function. And you can see that in both simulation and experimentation. But of course, if you Gaussian apodize the array and then take the Fourier transform, then of course you end up with a Gaussian distribution in the far field which you can see by this blob. But you can see it's much smoother than the sinc function. So if you have the ability to control both the phase and amplitude in your phased array, then of course you have complete control over the optical field. So the question is, when am I going to have my Princess Leia emitting R2-D2? And of course that's kind of far out. But actually, it is something in a way. It's obviously not going to look like a emitted Princess Leia, but it is something that we are working on in the infrared. So we are hooking up our phase shifters to 3D integrated CMOS. And in fact, to make it active, but in fact, even if you think of the MIT logo, that was actually not a flat MIT. That was a curved MIT in space. So it was already holographic. So I think this is actually a really interesting application. Of course, it becomes more interesting when we go to the visible, and there's certain challenges there, getting to visible phase shifters, for example. But if you can get there, not only is there a market, you can imagine if you had a three-dimensional cell phone display, but that market would drive scaling of photonics in a way that communications never could. So you're talking about billions of elements integrated on one device. And you don't have to make an immediate jump to 10 billion elements. There are a number of applications that precede this. So this is for full 3D parallax. So that means as you move around the image, both up and down, left and right, that it looks sort of perfect. And if you've seen a really good hologram, they have one at the MIT Media Lab of one of these Russian eggs. And I swear, you look at it, you can't tell the egg is not there. You have to almost grab it to realize that it's a hologram. When you've seen something like that, you realize how compelling it would be to have this. And if you just move to 2D parallax, which means you don't get the 3D effect as you move up and down, you just get it left and right, that actually reduces the number of components by something like 3 orders of magnitude. So there are some intermediate steps. Just some other interesting new results. We just did this for fun on our phased arrays. This is basically we have a waveguide that's traveling, sort of traversing a circle here, and we are tapping off. Actually, I guess we're passing through each of these phase shifters and then tapping off a component of our light so that each of these emitters gets a different phase, and it's kind of linear. It's linearly changed as you go around the circle. So when you think of the emitted phase front, what you have is a corkscrew coming out, and if you draw a k vector off that corkscrew, you realize that a component of that k vector is now angular. So you end up with an angular orbital momentum coming out. These are then interferograms. So we have another component going through a fiber interferometer that's interfering with this emitted light. And you can see that we can change state from the L equals -4 all the way up to the L equals +5 orbital momentum state. And this is, you can see it's a little shaky because it's this external interferometer, but you'll watch it, you'll at least be able to see it changing sign here. So it's just flipping sign there and flipping back in the other direction. So it's mostly for fun, but it can be used for quantum because it gives you a nice basis for which you can have entangled states. More practically, we've been focused on implementing Lidar for autonomous vehicles. If you look at the autonomous vehicles that are out there today, and really all of the major auto companies have them, as well as Google is in this business somehow as well. If you look at them, they all have this Velodyne Lidar system that sits on top of the car. This is an image of the structure. It gives you this nice three-dimensional image of the surroundings. And the way it works is it actually has, they're one-dimensionally scanned, but there's something like 32 or 64 of these individual beams that are being scanned simultaneously. So you don't need full 2D steering, but you do need the ability to scan over a wide angular range. It works well, but of course, it's not the most attractive feature for your car, and it costs something like 4 times as much as the Prius that it's sitting on top of. So we're working on implementing Lidar, chip-scale Lidar that would sit in the 4 corners of your vehicle. Of course, you need a scan range of something like, it ends up being like 100 degrees per element because you need overlap between these different emitters. So the first challenge is getting a sufficiently wide scan range. And actually, this is one thing that I think silicon photonics has some advantages on, in that you can very tightly confine the optical mode. And because you can very tightly confine the optical mode, you can place these emitters very close together. And placing them close together is what separates the orders and gives you the largest scan range possible. We've implemented this as a full Lidar system, although we don't have Lidar results at the moment. So the idea is that it's a coherent system. You have a transmitter transmitting a beam out, and you have a receiver aperture that's also pointed in the same direction. And generally, we want to avoid using optics, so you have to have fairly large apertures to do this. But our results at the moment are really about high speed and wide angle steering. So this is over 51 degrees, and you can see it as it speeds up. And what's happening is it's going faster than the camera can respond, and then the beam collapses down. And of course, when it collapses down, you've reached the 3 dB bandwidth of the phased array, which is about 100 kilohertz. Just some other applications. We're working on heterodyne interferometers. So these are interferometers that are measuring displacement based on a shift in the phase of one signal versus another. We put a laser beam through a beam splitter. We then upshift one component by F1, another component by F2, beat them together. That gives us a reference signal, this yellow signal. We then send the 2 components out, one to a, drawing is a little bit strange, but one to a reference. One comes in here and goes to a reference detector, and the other one goes out and reflects back off of a mirror, interferes with the one that's going to the reference detector, and that gives you the signal phase. And so as the position of this mirror changes, the phase of that signal changes, and we've shown that we have accuracy to within something like plus or minus 7.5 nanometers or so at the moment, although our stage is about this accurate as well. This is just a showing that the single sideband modulator performance, we can shift our frequency plus or minus by something like 10 gigahertz. Just quickly, I think a compelling area to look into is microwave photonics. Of course, so we have I think there's one reason for this, and there's many reasons, but one reason is that you can tune your filters very effectively. So you can tune, this is a new result that we have, where we can actually tune a ring losslessly over the free spectral range. And then you also have things like very high Q resonators, and I guess our resonators are not as high Q as yours are here, but they are in silicon. They're very high Q, so they're about 10 megahertz. But the combination of both very high Q and the ability to actively tune structures makes for an interesting application to microwave photonics. And then as we've been working on implementing low phase noise oscillators on chips, this is work that really, at least in our configuration, stems from the NIST frequency divider approach, where they recently showed, in fact, that they really have better noise performance than just about any microwave oscillator out there, at least in the close-in phase noise. And sort of overall, they're doing quite well. And this is interesting because of the fact that if you look at a microwave sapphire-loaded oscillator, sapphire-loaded crystal oscillator, they tend to have to be cryogenically cooled. They're large, they're bulky. And while the NIST result is still large and bulky because it's on a tabletop, fundamentally, when you look at the performance of the microwave oscillator versus the optical oscillator, initially they look fairly similar. Leeson's equation and Shallow-Towns equation are more or less the same, except we're replacing KT by HF, which is actually larger than KT. But the fact that you can have a very high Q and the additional fact that you can use frequency division when you use a mode-lock laser means that actually fundamentally you should be able to do better with an optically generated oscillator. So this is our pictorial of what we're trying to do under the DARPA E5 program. It's somewhat complicated, but it is a frequency divider loop where we have a CW laser locked to a frequency or an on-chip frequency reference, and then we have a mode-lock laser, which then locks to the CW laser. One line locks to CW laser. We then generate a second line off the CW laser and lock that to an adjacent line of the mode-lock laser and beat them together on chip. Just to finish up, I think sensors is another area that is still very compelling. This is some work on a thermal detector that we implemented some years ago. The device works on the thermal optic effect. Silicon nitride actually absorbs nicely from about 8 to 14 microns. And so if you have a 10 micron illumination, you absorb some of that 10 micron light. If you're suspended, you're very thermally isolated. That shifts the resonant frequency, and you can interrogate it at 1.5 microns, where silicon nitride is transparent. The fact that there's no actual resistive element in this device, and I'm referring to that because bolometers would be the comparative component, means that you have fundamentally better noise performance because you have no Johnson noise in the element. You also have an easier time thermally isolating the structure because you don't have any metal contacts to it. And because you have this very high Q resonance, it means you have a very large responsivity. So very quickly, we were actually able to hit the thermal noise floor in these devices. And I think it's a compelling application for scaling because, of course, if you wanted to make an imager, you would have to get to millions of elements. So with that, you're now sitting sort of in the same place as the Intel engineers some 40 years ago, where we've gotten to about 10,000 components on chip. And so you can ask yourselves whether you think photonics will scale to the millions or billions of elements. Personally, I think we'll get to the millions of elements, but it remains to be seen which technology will drive it forward. Happy to take any questions, my colleagues in funding.
Questions? Yeah.
Two questions. So in the phased array systems, the grating antenna, does it emit only in the upward direction or simultaneously both up and down?
Up and down. So we're losing half of our light in the downward direction.
Okay.
And that's easy, relatively easy in principle to correct. Practically, it's a pain in the neck, so we've left it alone. I mean, you can put a reflector below at the right distance, but when you're starting with SOI, it's painful.
Are you using free carrier diffraction within the phased array antenna as well, or are you just using thermo-optic effect?
Just thermo-optic. I mean, on a 1D phased array, we could also use PN junction-based devices, and we could make them even faster than the 100 kilohertz result. But we're just using thermal effects.
Michael?
In your microwave oscillator, when your mode-lock laser, what would you use as a satellite absorber?
So right now, our satellite absorber is pasted on. Okay, so it's, and actually it's been the biggest problem for our mode-lock laser.
Is it a semiconductor then?
It is. It's a semiconductor satchel absorber. That's the biggest problem is that practically you have to have a nice vertical flat surface that's polished well to put this thing on there, because with erbium we have very low gain, and so if you have a component with 3 dB of loss, even that's problematic inside the cavity. So we're now thankfully through that problem and just dealing with dispersion issues. But we have mode locking. It's just that it's kind of it's Q switching at the same time.
You had something like 20 or 30 levels of photonic layers you're talking about. Are those
Yep.
bonded on top of each other, or are those?
When I say that, I mean those are mask levels.
The mask level? Okay.
Yep.
If you don't mind running back to about slide 33.
Yes.
I guess it was maybe before that. When you had the amount of power required for your transmitter.
Here.
So you get the laser plus modulator as being about, what it is, 18 femtojoules. That's so how much? What's included? Is this just the erbium laser, or does this include the off-chip pump laser?
That would include the off-chip pump laser, but this is taking me back a while as to where this, how does it get to be that low? I think the receiver is a big part of it. So the assumption there is you're getting to minus 28 dBm sensitivity.
Even so, that number doesn't look right to me, right? I mean, if you've got, it's hard for me to imagine that your external pump power itself will be less than 10 milliwatts.
Well, okay, no, that's true. I mean, but the assumption here is you're driving many links simultaneously. So it's not just one pump for one link. It's one pump divided. So what matters is the efficiency of the pump rather than, I don't even think you would have a 10 milliwatt pump. It's probably much higher than that.
That was my assumption.
Yeah. So.
Your comparison to DFB was a little unfair, I think. You suggested that DFBs were 1% efficiency.
Telecom DFBs. Telecom
I don't
DFBs.
think that's true anyway. But, so I think certainly.
If you look at a telecom DFB and you look at the spec sheet and you put it at a 50-degree C case temperature, it's less than 1%.
So there's very little difference between a DFB and a pump laser. So if your conversion efficiency is 100%, then they'll be about the same, but this won't be 10 times worse. I think you could argue that in fact this is always worse because your efficiency is not 100%. But DFBs can be quite efficient, not any worse than pump lasers, I don't think. So certainly.
I think the difference is that you have to cool the let's say telecom DFBs, you cool them, right? And that's I think that's the current assumption. And so if you look at a telecom DFB, then you're cooling it. If you're using a off-chip pump, they're uncooled today. Now, it's not to say you couldn't make a DFB that's also uncooled. So it's just looking at, so looking at today's telecom DFB lasers.
So if you assume that this doesn't need a TE cooler and that must have a TE cooler, then you might get a little close. Then 1% is not too far off necessarily. But you can really make a much better than 10% efficiency telecom DFB. So.
Sure, they haven't been driven for that purpose, I think.
Okay. Other questions? All right. Thank you very much, Michael.
Thanks.
Yeah, actually, make a point you're including the TE cooler in there. So.
Yeah. I think I normally state it, but now I've got so many slides in here that I'm like trying to